Okay, guys, as you can see on your screens, we are doing Unit 6 practicals, okay? And this is the first practical on Unit 6, which is called Practical 9, okay? It has been requested to me many times before, and I was very skeptical about doing videos on Unit 6 because, okay, core practicals means doing an actual experiment, but I cannot do it on my iPad screen. But I can nevertheless walk you through the core practical, okay? So we will dive in and I will upload the video and you can tell me in the comments whether you like it, whether it's useful. You may make suggestions about things I can change or improve and so on. Okay, so I really appreciate those of you who write comments, by the way, because it helps me to modify things and try to make better videos. Okay, so core practical 9 is about investigating the relationship between the force exerted on an object. Okay, so the force exerted on an object and its change in momentum. Okay, so in mathematical language, this means F times delta t, which is the impulse, is equal to the change in momentum. Okay, so we have a force F acting on an object for some time delta t. Okay, and this is supposed to change the momentum by delta p. Okay, so which is that force? Let's look into this apparatus over here. So the force is provided by these masses m. Okay, so force is m times g. Okay, and these are variable masses. Okay, so we can remove one of these and change the mass accordingly. Okay, so and this is a taut. Okay, this is a taut string, and we also need a pulley. Okay, and we have a cart with mass m, capital M, okay, to distinguish from the m times g. Okay, and how can we measure the time that this force was acting on this trolley? We can pull the trolley back. Okay, so this L here is a variable. I mean, we can pull the trolley back, and as we move it back, we can measure the time needed until these masses drop to the floor. Okay, you have to time it so that you stop the clock right before these masses reach the floor. Okay, so F is given by lowercase m times g, and delta t is given by the time taken between the trolley starting from rest. Okay, so you will pull it, I don't know, maybe here. Okay, so this is your trolley. You will pull it back here. You will start the timer, and right before the masses hit the floor, you will stop the timer. Okay, so you will know this delta t over here. Okay, a better way to know this delta t is to put a light gate, and you will see what I'm trying to say. Okay, so this is a light gate that looks like that. Okay, something like that. Okay, I cannot draw it perfectly, but okay, you can put a light gate there in a way that it doesn't intervene with the trajectory of this trolley. Okay, so the light gate can serve two purposes. Okay, it can actually accurately measure delta t, because you can use it as a stopwatch. Okay, so you can set it so it becomes a stopwatch, and it measures the exact time when, okay, it will start from 0, so time will be 0 back here, and time will be delta t once the trolley passes through the light gate. But you also need to determine the velocity of the object, which is the second part, the right hand side of this equation. Okay, because delta p is nothing but m, capital M, right, because it's the mass of the trolley, times delta v. Okay, and what is delta v? Delta v is the initial, the final velocity minus the initial velocity. Okay, but the initial velocity is 0 because we will start the trolley from rest, so we only need v final. Okay, how can you determine v final? So if you look at the trolley, there is this, I don't know, let's say it's a cart of length d. Okay, so when this car passes through the light gate, it interrupts the light gate, so it can both measure delta t, the time needed for the whole trip, but it can also measure the time needed for this car d, which is really small. Okay, I mean d, for example, L might be like I don't know, 5 meters, whereas d might be like 0.1 meter, 10 centimeters. Okay, so it's a small car. Maybe it's smaller than that, maybe 0.05 meters or something like that. Doesn't matter, but it helps you to measure the final velocity by dividing d, the length of the car, over, let's call it delta t2, okay? And delta t2 is the time needed for this car to go through the light gate, okay? And it's different from this delta t that we mentioned in the beginning. This delta t goes into the left-hand side of the equation, whereas the delta t, the time needed for the cart to pass through the light gate, is delta t2, and it helps you determine VF. Okay, and this is the experiment, and we are done with the video. No, I'm kidding. So this is the general idea, but let's write things down a little bit more formally. So the goal again is to determine delta p, the change in momentum of a trolley when a force acts on the trolley for a time interval delta t. Okay, the equipment needed is a trolley, slotted masses plus hanger, okay, which is this part of the experiment. I mean, these are the slotted masses. The slotted masses are what we call the lowercase m, okay, and those are the masses that provide the force that accelerates the trolley, pretty much. Okay. Okay, we said that a pulley, string, a light gate, a meter ruler, okay, a stopwatch. Okay, this is another way you can do the experiment. You can think of the light gate as the one responsible for measuring the final velocity, okay, by measuring this time delta 2 needed for this cart to go through the light gate, okay? And you can use a stopwatch to measure the time between the cart being all the way back here with velocity 0 until these masses almost hit the floor, okay? Which determines, so you can use the stopwatch to measure delta t pretty much, whereas the light gate might be used to measure delta t2. Though the light gate can actually measure both delta t's that you need in this experiment, but okay, that's fine. You need a runway, even though we are not talking about a plane taking off, but you do need a runway. And you need the mass balance or something to measure the weights, pretty much, okay? The weights of both the trolley and the slotted masses, okay? Now, okay, let me check my notes real quick because I don't want to make any mistakes. Okay, so the variables in this experiment. So the variables, let's talk about which are the variables that we need to take care of and measure and so on. So the independent variable is the accelerating mass what's wrong with my English? So it's the accelerating mass m, okay, which is the hanging mass. Okay, the dependent variables. So this is the independent variable. Dependent variables are the time to pass the light gate, which is what I call delta t2. Okay, this is what is used to measure the velocity of the object, and the time for which the force acts. Okay, and this is what we call delta t. Okay, and there are some control variables. Okay, which, as the name suggests, you need to keep them under control so they don't interfere with your experiment. But these variables provide the randomness in the experiment. So when we talk about random error, we involve, sometimes we mean things like this. So control variables, okay, ideally they shouldn't intervene with your experiment, is the overall mass of the system. Okay, so M pretty much, okay, the trolley. And the tilt angle of the ramp. So these are variables that affect your experiment, but they shouldn't, because you set them up once and you work with the experiment then after you set them up, okay? The size and length of the cart, and we are talking about this cart, this one, okay, that is used to measure the time needed for the trolley to pass through the light gate, okay? Okay, what else? And we must use the same trolley for all experiments. Okay, the method is what we discussed earlier. So the method is, let's go back to the scheme. We will basically pull the trolley back and let it fall and measure delta t and delta t2, okay? And we will do this for multiple lowercase mass m, okay? So we will change the mass, measure delta t2 and delta t, and keep going until you have enough data points, okay? So, all right. So basically, so the method, maybe I can write a few things down. So set some mass m1, measure f times delta t and delta p, which is equal to uppercase m times v, okay, which we call v final, okay. And so f delta t is equal to mg, so m1 g delta t, and delta p is m times v final. Okay, and then repeat for 3 to 5 different values of m. Okay, so recall that if this works, I mean, if f times delta t is equal to delta p, this means that m times g times delta t is equal to m times v. Okay, so if you plot m times delta t as a function of v, okay, so if we solve this for m times delta t, we find m over g times v. Okay, so if you make multiple, if you measure delta t for multiple values of m, and then you record v, okay, and you plot this, so if you plot m times delta t versus v, it will look like this. So m delta t, and then you will have v here, and maybe you will have some data. So this should look like a straight line, okay, and the gradient of this line, so if you plot this, you should get a straight line with gradient equal to m over g. Okay, so g should be equal to m over the gradient. Okay, we said we already said it, but we didn't write it down, so let me write it down. So measure, okay, no, this is not the proper way to say it. So take measurements for at least 5 values of m and the corresponding values delta t and delta t2, and I remind you that delta t2 gives you v. Okay, and what else do we need to mention? Possible uncertainties. Okay, oh, and you will of course use a balance to measure m, uppercase and lowercase m, and so on. So let's talk a little bit about the uncertainties involved in this experiment. So I hope this is clear. I don't know what else to say, but the gist of this experiment, of this core practical, is to verify that f delta t is equal to delta p. Okay, now uncertainties involved, uncertainties in this core practical is one, the length of the cart. So you will measure this using the ruler. So measure okay, measure using the ruler. Okay, and maybe it's 10 centimeters. So you measure using the ruler, and then the error is going to be plus or minus 1/2 the smallest deviation of the ruler. So for example, maybe you measured it to be 10 centimeters plus or minus 0.05 centimeters, okay, because in this case the smallest deviation is 0.1 centimeters. Okay, If the smallest deviation is 0.5 centimeters, okay, use 0.25 for your uncertainty, okay? So the absolute uncertainty, the absolute uncertainty is 0.05 centimeters. Now the percentage uncertainty, which we can also say write as percentage uncertainty, is going to be, in this case, 0.05 over 10 times 100, so that's 0.5%, okay? So number 2, for the masses, okay, let me think. Okay, you can assume 0%, or if you use imbalance, use the smallest, use half the smallest deviation of the balance. Okay, so for example, if the trolley is like 0.5 kilograms and your scales have a smaller deviation of 0.1, then you have to use 0.05 kilograms, okay? All right, 3, and perhaps most important is the uncertainty in delta t, the time that the force was acting. Okay, we take this from the stop clock. So the best way to take this measurement is to repeat a measurement. So the same measurement for the same weights, I mean. So repeat a measurement for 3 to 5 times. Then take the average. And the uncertainty will be equal to the half range, okay? So, for example, if delta t is 2.33 seconds, the first time you measured it, the second time is 2.01 seconds, and the third time is 2.64 seconds. This is an exaggerated example. The mean will be 2.33 seconds, and the half range will be equal to the maximum value minus the minimum value over 2. The maximum is 2.64, the minimum is 2.01 over 2, gives us 0.32 seconds. Okay, so you see that if you use a stop clock, okay, and it's important to mention this now, if you just take one measurement, okay, then just use half the smallest deviation of the stop clock. But the best way to handle this is to, again, let's go back to the apparatus. Okay, let's say that you pull your trolley back here, okay, and you have some certain mass m hanging there, okay? So the best way to eliminate the errors in measuring this delta t is to repeat the exact same setup, meaning pulling your trolley back to this point, okay, that I'm showing there in the screen, okay, using the same mass, and measure for 5 times, 3 to 5 times. I know it sounds tedious, that's why I'm not an experimental physicist, I studied theoretical physics, but this is the proper way to do it, okay? Now, okay, we came back here. Where are my uncertainties? Over here, okay, 0.32. Now let me show you how you find the percentage uncertainty for this measurement. So the percentage uncertainty will be 0.32 over 2.33 times 100. It gives you a 13.73% error, which is large, okay? And the fourth and final source of error in this experiment is, as you guessed, the time ₂ that the trolley, actually the cart, yeah, needs to go through the light gate. So assume this to be small though. So this is small, larger than 0.1% error. Okay. So if we combine all these uncertainties that I mentioned here, so combining, so let's say that you're, okay, how would you combine? So combining uncertainties. Let's say that you want to calculate the uncertainty in the gradient, okay? So the gradient, as we said, back here in our nice plot that we made, the gradient is equal to m over g, right? But it's also equal to, let me see. So remember that we said that m times delta t is equal to m times v, and I forgot the g there, so m times g times delta t, okay? And if we plot m times delta t, let me think. Oh, sorry, let me repeat this. So the gradient should be equal to m over g, but the gradient, don't forget that the gradient is equal to this part over here, to m times delta t over v, right? So the gradient, so forget this, and just, we can also, the gradient should be equal to this capital M over G, but the gradient is actually equal to M delta T over V, okay? And there is an error in that small case, in that lowercase m mass, there is an error in delta T and an error in V, okay? So if we combine uncertainties, taking the gradient to be m times delta T over V, then the percentage uncertainty in the gradient, and the reason why I'm calculating the percentage uncertainty is because we are having the division of variables, okay? Watch my videos on uncertainties and I hope you will understand. So the percentage uncertainty in the gradient is going to be the percentage uncertainty in the mass, which we took to be 0%, okay? Plus the percentage uncertainty in delta t, which we took to be 13.73%, plus the percentage uncertainty in V, which we take to be 0.1%, okay, which we take from here. So the total percentage uncertainty will be 13.83% for the gradient, okay? And if you want to calculate the absolute uncertainty in the gradient, all you have to do is to multiply the percentage uncertainty in the gradient times the gradient itself, okay? And this is core practical 9. This is it. I mean, these videos are gonna be short, I guess, but one more thing I want to stress is that in unit 6 they don't necessarily ask anything that comes from core practical 9 per se, or core practical 10, 11, whatever. They usually ask things that involve uncertainties. So You have to put a lot of emphasis into understanding uncertainties. Again, I have a video, go watch that. And what they really want you to understand is the physics behind an experiment. So for example, they might actually have a problem related to F times delta T equals to delta P, which will not involve anything from what we discussed in this core practical 9. But they will expect you to understand that this should be true, and then they will show you some relevant experiment that might be similar to the one we just discussed. It might not be similar, okay? But they expect you to understand the physics, okay? So if you understand the physics and uncertainties, okay, you cannot skip that. That part is really important. You need to understand uncertainties, okay? So, but nevertheless, let me know what you think about this video. This is how I plan to make more videos on core practicals, okay? So your feedback is really valuable for me because I try to improve on how to make videos and so on. And I have plans about other content that I might share related to physics and maybe life and stuff like that. So yeah, I'm gonna stop here. Please like and subscribe, as they say, and see you in the next video. Bye.